Alright, welcome back. This is homework 4 in our Thermodynamics 1 course. This is first law analysis on closed systems. And our first problem is you have 20 moles of an ideal gas, initially at 250 kPa and 300 Kelvin. You apply heat to the system to raise the piston of a piston cylinder apparatus. Okay, so I have a piston. P1 equals 250 kPa. T1 is equal to 300 K. Cp is equal to 7 halves R. How many moles was it? 20 moles. 20 moles. Okay. 20 moles. Okay. And you apply heat to raise the piston of a piston cylinder apparatus by 20 centimeters. Okay. So this goes up by 20 centimeters. Okay. Delta H, I guess, or, well, delta V divided by area would be 20 centimeters. Okay. Area is 0.1 square meters. I want to know how much heat it needs to do this. Okay, so I've got Q going in here and all these other things. Okay, so I've drawn my picture. I put everything I know, and I put what I don't know. I should draw a boundary. Okay. What's the third thing I need to do before I really start? I need to start doing assumptions. Now, do I need to do all of my assumptions now? No, because some might come up as I'm doing it. I might realize, okay, oh, I'm going to need to assume that, or probably appropriate to assume that, or whatever. But the ones that seem immediate right now, okay, it looks like our heat capacity is constant. Let's see here. I think it said an ideal gas. Yes, it does say an ideal gas, so I'm going to assume an ideal gas. I'm going to assume it's a closed system. There's no leaks or anything. I'm going to assume delta KE and delta PE are approximately 0. I'm going to assume no shaft work. Okay. There's definitely boundary work, and there might be other forms of work, but probably not. Let's see here, there's definitely heat transfer, because it's not adiabatic. I think for now those are some good assumptions. Something else may come up. Okay, so first I need to do a mass balance. Now, it's kind of obvious that the starting mass is going to equal the final mass, and I don't really need to do a mass balance. But it's just good practice to do one. Okay. And so my mass balance is, in m dot I minus summation of exits m dot E equals dm dt of my control volume. Okay. Well, there's no ins and there's no outs because I'm a closed system. So I have dm dt, control volume, equals 0. I do some integration, I've got m2 minus m1 equals 0, and so I have m2 equals m1, which is going to equal m, same thing with moles because I don't have any reactions or anything. Yeah. Now I need to do a energy balance. Okay, so I have sum of n dot I hi plus 1/2 v squiggly squared I plus gzi minus summation of n dot E he 1/2 v squiggly squared E plus gze plus Q dot plus work dot equals du plus EK plus EP d time my control volume. Okay, well, I don't have anything coming in. I don't have anything coming out. I do have some heat, obviously, because that's what I'm trying to find. I have some work. I'm not steady state, so this whole thing stays, but my delta E and my delta P are pretty much 0. Okay. So when I'm all said and done, I have Q dot plus work dot equals du dt, my control volume. I don't really care about time. I don't care about how long this takes or anything like that, so I can just integrate this to say, you know, the total amount of Q plus the total amount of work is going to equal the change in U. Okay. Now, again, this is a capital U, not a small u, so it becomes md little u. Okay. Let's see here, what else? Okay, so if I rearrange this, I'm going to have Q is equal to plus PdV, because my work is minus PdV. When I move it over, it's plus from V1 to V2, plus M, or N in this case, CV dt, okay, from T1 to T2. Okay. So that's really my kind of working equation right there. This, you know, I applied the ideal gas law, and I'm going to need to do some other things, but we'll get there. Okay. Alright, so I'm going to erase most of this. Okay. Alright, well, we've got this work term, PDV. You know, there's the different cases that we can apply. We can assume it's isothermal, we can assume it's isobaric, we can assume it's isochoric, we can assume it's polytropic. In this case, well, you know, you've got, you know, it's a freestanding piston cylinder, so we can assume that it's isobaric. Okay. So that is an assumption that we want to apply, and so my Q is going to, we're already assuming that Cp is constant, so Cv is going to be constant as a result. Okay, so this becomes, you know, P dV, V1, V2, plus NCV, T1, T2, dt. Oh, well, those are just normal integrals, and so I can just solve them as normal integrals. So my Q is going to equal, you know, P times V2 minus V1 plus NCV T2 minus T1. Okay, my volumes, okay, if I want to simplify this even further, you know, this would be P times the area times my delta, you know, again, my delta height, okay, well, delta V over area, so, so this is kind of my, you know, change in height, we'll call it HT for height, or maybe change in Z, that might be okay. You know, plus 5 halves are times n delta t, t2, t1. Okay. So it doesn't really say how much the temperature changes. Let's see here. Does it say how much the temperature changes? No, it doesn't say how much the temperature changes, and so we don't have enough information. We have this, we have the pressure, but we don't know how much the temperature changes, so we don't actually know the total amount of heat that's going to need to transfer to this. Okay, And so it's all dependent upon that change in temperature. So for the sake of the website, I'll change the problem to be, okay, the ending temperature is 350. Okay, now I have enough and I can solve this as normal. But really, the point of these problems though is to go through the motions and get to an equation. Okay, when you're out in industry and you're analyzing a system like this, be like, oh, I need a final temperature. Well, you just take the temperature at the final state, and it would be that easy to figure out how much heat is being transferred.